like that?
No.
Okay. Good, Mackenzie? Enough?
Yeah, I'm good.
All right. Cool. Okay, so we're going to talk about something today that it's a little bit like, I don't know how to describe it. It's kind of a thinking section. I mean, there's math to it, but it's a little bit more thinking. I want to make sure that I've got my chat up here to the side. All right. So what we're going to talk about doing today is something called mathematical induction. Okay. So I'm going to kind of read it to you because I think if you kind of hear it and see it, it kind of helps to determine what it is. So here's the principle of mathematical induction. Okay. So if you have P sub n is some statement involving the positive integer n, okay? If P sub 1 is true and the truth of P sub k implies the truth of P sub k plus 1 for every positive integer k, then P sub n must be true for all positive integers n. So when I read that, you guys totally got that, right? Totally makes sense. All right, Greta just invited me to join her hangout. All right, she's going to watch it. Okay. I'm not sure why it's not letting her in. All right, so mathematical induction is basically the idea, if I can explain it in the most basic way, is that we're saying that if you can show for a series of numbers, a sequence of numbers, like if you can show that the first number is true, which is pretty easy to do, and that every number after that tends to follow or follows the same pattern, then we can assume it is true for every number that keeps going out from that. Okay, so basically, when all of these places where we had, some sequence of numbers, and we just assumed that the sequence kept going on forever and ever, this is a way of like induction. So it's basically saying that because you're able to verify that this pattern is working, then we can assume that it's true for all the positive integers in that sequence. Okay, so it's kind of proofish, a little geometry. I mean, you're not doing geometry, but it's like that idea of wanting to prove that it's true. If that makes sense. So to actually do this idea of mathematical induction, you need to basically do this little paragraph down here. So to apply this principle of mathematical induction, you need to be able to determine that the statement p k plus 1 for a given statement p sub k, and then determine if it's true. So I think this is one of those things that sounds like kind of crazy. And I mean, it's like not crazy, but just sounds like, huh, when you read it. But I think when you see it, it'll sort of make sense. Okay. So like your book likes to do, they like to kind of baby step into this. Not baby step, but they like to give you like, I don't know, I guess it's baby step. They give you all the different pieces and then kind of at the end you do it all together, if that makes sense. I think I just opened that in Paint, didn't I? Maybe I just copied it. Okay. So what I mean by like baby stepping into it is not drawing random black lines. Is that one of the parts of mathematical induction that is important is that we need to be able to figure out what P if we have some p sub k, if we have some value, we need to be able to figure out what pk plus 1 is. Okay, and so you'll see here the first few problems, they give you some p sub k, and they want you to figure out what pk plus 1 is. So like I said, this is where you're kind of doing something that you don't quite know why you're doing it yet, but you will later. All right, and this idea of being able to figure out what k plus 1 is has to do with this second principle of mathematical induction, where if you have p sub k, then it implies the truth of pk plus 1 for every positive integer. So it has to do with that. We just haven't quite gotten to that part yet. Okay. All right. So for 2, 4, and 6, we basically just need to find out what pk plus 1 is when we have some pk. Does not stand for penalty kick, right? There's just weird letters that I have to keep saying over there. PK sub. Okay, so in number 2, okay, number 2 is right here. PK is 4, and then k plus 2, k plus 3. So if we want to figure out what pk plus 1 is, right, we are going to plug k plus 1 in for k everywhere in our equation. So we've got 4 over, instead of k, we're going to write k plus 1 plus 2. I'm going to run out of room, aren't I? And then we have times k plus 3, but instead of k, we're going to write k plus 1 plus 3. All right, so let's simplify this, and we get that it is 4 over k plus 3 times k plus 4. So for this particular one, not too bad, right? pk plus 1, p sub k plus 1, is equal to 4 divided by k plus 3 times k plus 4. Okay? So then number 4, a little bit trickier, but not too bad. Number 4 is that p sub k equals 2 to the k minus 1 power over k factorial. And these factorials are going to come back, right? So pk plus 1, oh, that doesn't even look like a k, would be 2 to the k plus 1 minus 1 power over k plus 1 factorial. So we would simplify this as 2 to the k power over k plus 1 factorial. Okay. And then number 6, they write it a little bit differently, but the idea is the same. So actually, I don't know if I have number 6 written down right. Oh, no, it's okay. All right, so for number 6, I always want to do that. Figure out how to erase at some point. Okay, so So number 6 is a little bit weird because that's why I had to do a double take at it. So P sub k equals 7 plus 13 plus 19 plus blah, 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 plus 6 times k minus 1 plus 1 plus 6k plus 1. So for this one, what you're going to do is you're going to say that pk plus 1, you're going to look at this last term here, is equal to 6 times k plus 1 plus 1. So it's going to be your p times k plus 1. Okay, so we got that going on. That's figuring out what the next term is. Again, I just want to write on there. All right. Let's look at number 8 now, where we're actually going to do mathematical induction. It's not too bad, at least in these first few problems. Okay. So let me grab number 8 here. Okay, so number 7 through 20 says use mathematical induction, which we're only going to do through 13. Use mathematical induction to prove the formula for every positive integer n. Okay, so what they're saying is that if you have 3 plus 11 plus 19 plus 27 plus 8 times some number minus 5, if you add all those together, you're going to get n times 4n minus 1. Okay, so what they've done is they've taken this sequence of numbers and they've added them together and they've come up with a formula to tell you what the sum is when you add these together. I just want to kind of make sure that we get that. So, for example, if you wanted to add up the first 4 numbers that were in this sequence that are already written out here, right? It would be, so this is the first 4 numbers are 3 plus 11 plus 19 plus 27, which happens to be 30 plus 30. So if you add those together, you get 60. Okay. On the other side, if I do n times 4n minus 1, and in this case, it's the first 4 terms. So 4 times 4 times 4 minus 1. So 4 times 16 minus 1, or 4 times 15. Sorry, 4 times 15. I end up with 60. So just kind of my little check shows me that, yes, this is a way to write the sum of all the terms in the sequence, right? And this happens to be a arithmetic sequence that's getting added together. That's great that I'm able to do a quick check, right? But what I want to do is I want to use what the book asks me to do is to use mathematical induction to show that it's true. Okay, so let's do the 2 steps of mathematical induction to see that if this is true or not. Okay, so the first step in mathematical induction is P sub 1 true? Is P sub 1 true? Okay, that's what we're going to do, the first step. So is P sub 1, is it true? So in order to figure out if that's true or not, we know that P sub 1 is when your number n equals 1, right? So this is your equation. So when I have 1 times 4 times 1 minus 1, does that equal 3? It's kind of like we checked P sub 4, but to do mathematical induction, you have to check P sub 1, okay? So let me get rid of this n equals 1 here, move it over here. Oh my goodness. Just move that over here. Okay. So if I have 4 times 1 minus 3, that's 3 times 1, it equals 3. So 3 does equal 3. So our first term is true. So the first part of our check for mathematical induction is true. Okay. The second thing is that P sub k implies the truth of P sub k plus 1 for every possible integer, then P sub n must be true. Okay, so this is where it gets a little bit more, I guess, complicated, you might say. It gets a little bit more complicated. All right, I hope that I'm going to try to explain this the best that I can. Okay, so this is step 2. So right now we have that 3 plus 11 plus all this stuff plus 8n minus 5 equals n times 4n minus 1. Okay, I'm going to consider this right here. This is your P sub k, and this is your, P sub n, I guess, if you want to call it that. Okay, to do step 2, you have to check for P sub k plus 1. So plus 1 more. Okay, so on my left hand side of my equation, I need everything that was in P sub k before, right? Plus, I need my next term, because what I'm doing is I'm doing pk plus 1. So I'm doing the next term in my sequence. So my next term would be, I take this 8n minus 5, right? My next term would be 8, and instead of n, I'm going to do k plus 1 minus 5. So what I've done now is I've made the next, so this is my current sequence, or my current series of numbers that I'm adding together, right? I'm adding the next number on, and I have my P sub k value of my series. Okay. I need to verify I need to verify that this equals k plus 1. So anywhere that I have this n, I'm replacing it with k sub 1. K plus 1 times 4 times k plus 1 minus 1. I need to verify that those equal each other. Okay. All right. So then what I'm going to do is on my left-hand side, for this P sub k, I'm going to replace that by 8k plus, 8k sorry. I'm not going to replace it. Hold on just a second. I want to double check my notes before I tell you this. Give me 1 second. Let me double check before I tell you. Okay. Yep, I just wanted to make sure that I was going to tell you the right thing. Okay, so is everybody sort of okay with what I did so far?
Yeah.
Okay. Mackenzie, are you kind of okay with that so far? I'm trying to find the next term in my sequence. So I'm taking like my original, this is the red part is represented by this right here. And then the k plus 1 part, the next term is represented by these two purple things. I'm adding on the next term in my sequence.
Okay.
Okay.
Yeah.
So the red is my original kind of thing that I had, and then the purple are the two next. So if I add one more term to my whole sequence on the left-hand side, then I need to add one more term to my equation over here. Okay, so I'm going to need some more paper. These two purple underline things I need to simplify, which we can totally do. So I need to simplify those two things. What I need to also do is I need to rewrite this p sub k in some value that I can use. All right, so I'm assuming this is going to be true. I'm assuming that this is a true statement, that they've told me that when I add this up that this is true, right? Oh, I don't want to use red there. So for my p sub k, I am going to use n times 4n minus 1, because that represents all the numbers that I've added up before I've added on my k plus 1. But instead of using n, I'm going to write it as k times 4k minus 1. Because that then represents all the numbers that I added up before I added my next term on. Okay, then I'm going to add my next term, which is 8 times k plus 1 minus 5 equals k plus 1 times 4 times k plus 1 minus 1. Okay, this looks scary, but it actually will work out. It will work out in the end. Okay, so what I need to do now is I need to do some simplifying. So my favorite property, I'm going to distribute my k over here. I'm going to get 4k squared minus k. I'm going to distribute my 8 plus 8k plus 8 minus 5. So my left-hand side is coming together. I'm going to keep going on my left-hand side, and I get 4k squared plus 7k plus 3. That's my left-hand side. My right-hand side needs some work. So I have, on my right-hand side, I have k plus 1 times, and I've got to do some distributing here, 4k plus 4 minus 1, so 4k plus 3, right? Then to simplify that, I need to FOIL. So I'm going to get 4k squared plus 7k plus 3. So all that confusing work, and we actually end up showing that if I add the next term on, then, so it's this back up here, up to the top. They say it much more elegantly than I can. The truth of p sub k implies the truth of p sub k for k plus 1 for every positive integer k. And so then p sub n must be true for all positive integers. So basically, we've shown by mathematical induction that this is a true statement. Okay. So should we do another one? I'd say so. Let's do number 12. We don't have to do the ones, we're just doing 7 through 13, so you don't have to do the ones with sigma there. I don't believe. Okay. So I have this sequence here. It's 2 times 1 plus 3 plus 3 to the second plus 3 to the third plus blah, 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 plus 3 to the n minus 1 equals 3 to the n power minus 1. I sounded like I said the same thing, but they're different. This is 3 to the n minus 1 power, and this is 3 to the n power minus 1. So I have this statement, and I need to prove that it is true or not true based off of mathematical induction. Okay, the first step is the easier step, right? The first step is that we need to show that P sub 1 is true. Okay, what is P sub 1? P sub 1 is when you take all this other stuff away and you just have your first term, so it's 2 times 1. So P sub 1 should equal 2, which should equal this side of my equation, 3 to the first power minus 1. So 2 should equal 3 minus 1, which equals 2. So P sub 1 checks out. We like that, right? Okay. The second part is that we have to show that basically P sub k plus the next term in your sequence, which is k plus 1, I'm kind of loosely writing this, equals P sub k plus 1. We basically have to show that if we add up all the stuff and then we add the next term on, then that equals the new sequence. Okay, so P sub k and P sub k plus 1 actually come from this side of the equation. All right, so this helps fill this in and this in. So P sub k is 3k minus 1 equals, over on the side, 3k plus 1 minus 1. That's where that part of your mathematical induction comes in. Okay, the k plus 1 part actually comes from here, which is your next term is 3 to the n minus 1 power. So this middle one actually comes from here. So it's plus, and instead of 3n minus 1, it's going to be 3k plus 1 minus 1. Okay, so we end up with 3k minus 1 plus, and then what is 3 to the k plus 1 minus 1 power? It's 3 to the k power, right? Equals 3k plus 1 minus 1. All right, what did I do wrong here? It looks different than my paper. 3k minus 1. Oh, I know what I did wrong. I forgot that this was all being multiplied by 2. Sorry, this one is being multiplied by 2. I forgot that out front. Something looks off there. That's being multiplied by 2. Okay. So, how am I going to make these two guys look the same? Well, let's see. I've got 3k plus 2 times 3k minus 1 equals 3k plus 1 minus 1. And somehow on my paper, I just was able to assume that that was true. What did I do here that... Give me just a second. Can you guys see how I might combine those two? I know you could pull out a 3k from both of those. Somehow on my paper, they just mathematically equaled each other. Magically. And I didn't write down my exact step how I did it. That was my bad. All right, Connor and Mackenzie, can you figure it out for me? Like, no, you're the teacher. You got to figure it out.
I'm not seeing where it went wrong.
I know. I'm like, what did I do? Okay, well, so what I did, just to tell you the truth, what I was doing really quickly is this is correct. Now I just got to figure out mathematically how to make them equal each other. The reason I know what's correct, here's my little side project. Oh, we're gonna go on a cruise. Is what I did for a little check to make sure that they actually equaled each other, that I didn't mess up with my numbers here, is I actually plugged in both sides of my equations. There should be a multiply here. Okay, so I did 3 to the x power, oops, I guess I need to write an x in there, 3 to the x power plus 2 times 3 to the x power minus 1. So I graphed that, and then I graphed 3 to the x plus 1 power minus 1. So they actually are the same thing. So I know that they're the same. So let me just think for a second mathematically. How did I just really easily pop that? Let's see. I could pull a 3k out of both of these. So if I do 3k, 1 plus, oh, that's what I did. Sorry. 3k times 1 plus 3 minus 1. So I pulled 3k out of both of those, right? Equals 3k plus 1 minus 1. Okay, what is 1 plus 2? That's how I got that. I got a random 3. It's 3k times 3 minus 1 equals 3k plus 1 minus 1, right? This is like 3 to the k power times 3 to the first power, or 3k plus 1 minus 1 equals 3k plus 1 minus 1. So they do work out. I knew they did. I just didn't know what. I guess I should have done my math, and then it would have shown me that it did it. Okay, sorry about the little rabbit hole there, but now that I have shown that P sub 1 is true and P sub k plus 1 is also true, then I can say that this is true by mathematical induction. True by mathematical induction. Okay. I'm just looking here what else we have to do. I think that's where we're going to wrap up for today. Unless we want to try, we could do number 10. Would it be helpful to do another one, or are you going to try them on your own?
I think I'll try it.
Okay.
And see how it goes.
Cool. Mackenzie?
Yeah.
All right. So remember, this is kind of the weird, this is the unmathematical way of saying what you're doing. You're taking P sub k and P sub k plus 1 from basically what the sum of all the terms together is. You're taking it from here. Okay, and that's how you're going to get these two terms. And then your value, your next value that you get added on is going to come from this equation. And don't forget, if there's like a multiply by 2 out front, it's going to come from 2 times 3 to the n minus 1 power. Oh goodness, we had somebody weird join our chat. Did you see that?